Hello, so today I want to talk about DLL hijacking, a particular flavor of DLL hijacking, but I figured I would give a overview of what it is, why attackers use it, a little bit of fluff text before we then go into the specific attack that I wanted to show today. So DLLs are dynamic linked libraries, and they are effectively exe files, but we don't execute them in the same way. Okay, they're not meant to be like double clicked in the same way that you would in exe, but fundamentally they are the same. The main difference is that they are built to be a collection of functions that other exes, other binaries on the system can use and call. So if anyone's familiar with like object-oriented programming and putting things into class and functions and things like that, that's what a DLL is basically. It's a binary that sits there to be to supply specific function calls to other exe files or other binaries or other systems on the computer. The reason why attackers can target these or would like to leverage these is because of a concept called living off the land. Okay, so whenever an attacker looks at a system, they can either try and put all of their tools onto it to try and do what they need to do, which is obviously very noisy. Lots of antivirus systems could then pick it up. Lots of other network systems could pick it up as well. But if they use inbuilt systems and functions, so things that are already installed on the operating system, on whatever it is they're attacking already, it can then help to fly under the radar because there's nothing additional being installed. There's less activity going on for them to achieve their objectives that could then get them caught. DLLs is one of the things that can be abused, and it's because of a thing called search order. Now, whenever a binary is being ran and it uses a DLL, it obviously needs to know where to look for that DLL, so where to find it. And if it isn't clear or if it's not sure, there is a predictable path that it follows in order to search for the DLL. And let me just pull that up and show you what that looks like. So I'll put a link to this article in the description down below, but this is actually the blog post that covers the specific DLL hijack that we want to do, but it does show the general flow by Windows when searching and loading DLLs. So it's got the directory from which the application is launched, the folder WinSystem32, WinSystem, Windows, current working directory, directories listed in the path and system path, and then in the user's path as well. So that's the typical way that the order loads, and an attacker can abuse this by potentially injecting their own DLLs in a higher search order. So let's say they know that the DLL that the component that they're attacking looks for is in Windows System 32. Well, they can then make a fair guess that it's going to check in the directory, the application directory first. And if that's a directory that they have a right access to, they then can then put their DLL into that directory first, run the application, or if the application runs automatically, and then whenever it searches, it will find a DLL in here that will be named the same, and then it will execute that instead. Now, a couple of downsides to this is obviously the application's functionality could break because it's not the actual DLL. You can get around that by doing things like DLL proxying. I'm not going to cover that in this video, but if you're interested, put a comment, let me know. I'll do a video on it as well. But what DLL proxying does effectively is it runs what we want and then it passes the request onto the actual DLL. So we basically sort of act as a inline attack in between the legitimate DLL and the application that's trying to call it. So that's one way we can do it, but in some cases we maybe don't care. Maybe it's some weird tool that it doesn't really matter if it doesn't work correctly, or it's something we can call ourselves. There's reasons for either or. But this is the general search order, but it doesn't always have to be that way. And the attack that I'm going to show here is abusing WinSxS, which I didn't even know this folder existed until I learned about this attack. So if anything I say about this folder structure or what it's used for is incorrect, let me know in the comments. And if anyone's watching this video, check the comments in case anyone has corrected me, because this is how we learn. But from my understanding, the WinSxS folder is SXS, sorry, I should say. It's basically like a backup folder for system files and system binaries. From what I understand, it's for in cases where, say you do a Windows update and something happens and it needs to revert back. The XSS folder, SXS folder, one day I'm going to say it correctly first time. That folder in particular, that's where it has the backup of the files that it can then restore and do things from. From my understanding, that is what that folder is used for. But the reason we care about it is that it has a different search order. Okay, so for whatever reason, exes in the SXS folder, the WinSxS folder, loads binaries or loads DLLs by looking in the current working directory. So let me pull up that page again. So as you can see, in a normal loading list, the current working directory is the 5th thing that it checks. But for whatever reason, binaries that are in that SXS folder check the current working directory first. Okay, and that is very, very beneficial for an attacker because the current working directory can, in theory, be anywhere. If we call the exe ourselves, if we call it manually, we can open a PowerShell window, create a folder called foobar, go into that folder in PowerShell, put our malicious DLL into there, and then run the exe that's in the SXS folder from that foobar folder, and then it will check there first. That might sound a little bit convoluted. I've got a demo set up, so I will show you how it works, and I'll also show you what it looks like from the EDR perspective, so the endpoint defense tool. In this case, I'm using Elastic Cloud, Elastic's endpoint protection, and I'll show you what the alerts can look like, what it can alert on, and where there's other things that it maybe misses, and sort of walk through that as well. So we'll get to the demo in a second, but the first thing that we need is a malicious DLL. And in this case, we've got 3 different flavors of this. So we have 2 Rust-based ones and one that's been written in Go. There's actually an exe. Just want to show you that it doesn't necessarily have to be a DLL that another binary loads. Sometimes it also loads other exes, which depending on the environment that you're doing a test in, that can be easier to run versus a DLL or vice versa. Okay, so it's just having different flavors of the same thing. So the Rust code itself is super, super simple. So we're bringing in the Win API create. This is obviously because we want to work with the Windows API. And in this case, it is using the message box W, and it's just going to open a pop-up box that says, hello, get hijacked. That's all this one is going to do. It's very, very simple, very straightforward. Okay, so it's just a proof of concept, just, hey, we did something malicious, or we could have, and that's all this function is doing. The DLL.main, the function name here. So if you remember, I'd said that you can't call a DLL directly, right? You can't just double click it as an exe. Now, where that presents a potential problem is we don't then have default functionality. Like whenever you double click an exe, there is a main function in there that runs anytime that's double clicked. But a DLL isn't made to run that way. So let me do a demo just to show what I'm talking about. So I've got my DLL that's been compiled here. And as I said, we can't just double click on DLLs to run them, but we can force them to run using run-dll32.exe. It's inbuilt in Windows. If you're doing this as a red team operation, probably don't use run-dll32 because every EDR under the sun watches it. But we can use it to sort of basically execute a DLL. And we have our DLL here. This is a slightly different version of this one, but the effect will be much the same. But all I'm going to do is going to run this DLL as is, just tell it to run it. We see nothing. Okay. And as I said, the reason being is that DLLs are collections of functions. So they're not meant to just be ran as standalone things. They're not set up that way. So what we need to do is we need to actually tell it the specific function that we want to call. And the notation for this is just comma and then the function. And if I run this, we then get our pop-up box. This is going to pop up a couple of times and do other things. Yeah, don't worry about that. We'll talk about what all that was doing in a second. So we need to be specific in the function call that we want to use. Now this can present a problem, because if I'm doing a DLL hijack, so I have an exe out there that I identified as calling a specific DLL. I'll show you how to do that during the demo. How do I know which function in that DLL it's using? And the short answer is we don't necessarily. Okay, now there are ways to find it out. Usually it's you need to attach a debugger or do some reverse engineering or things like that to try and actually see what is this trying to call. But programmers are lazy. People are lazy. So are security people. Not saying that I'm not. So there are common ones. There are ones that are recurring throughout. There's sometimes a DLL that maybe only has one specific function. What do they call it? And the usual is DLL main. Okay, in this, so capital D, capital M. DLL main. Okay, so we can guess, basically. And there are some lists online of other sort of common functions and stuff. And if you're targeting Windows-based systems, there's going to be a GitHub repo out there somewhere where someone's already reverse engineered it and you can just see which function calls it's using. But without knowing that, we would then have to try and reverse engineer the calls and things that are going on and try and figure out which function of the DLL it's calling, so that then we can name our function the same and it then gets called. Another thing to call out here, this is see, as I said, written in Rust. This no mangle is important as well. Now this was a little bit of GitHub Copilot helped me out here because my DLL main was not working, and it turns out that Rust does some funky things with the function names when it's compiled, particularly as a library. And this no mangle basically stops that from happening. So just that's why that's in there. That is an important piece that lets this function run. And then the wide null, this was again, GitHub Copilot. It tidies up the string, makes it nicer to pass between things, because the Windows API can be fussy with how the strings are formatted. So this just basically tidies up the format of them. As you can see, it's being called here whenever we're setting the title and text. Easy as that. Now, whenever you're doing this, we obviously want to compile this as a DLL, not as an exe. In order to do that, if I go over to the cargo toml file, you can see we're pulling in the dependencies, WinAPI, makes sense. But then we've got this lib create type cdy lib. Okay, and we need that in order to make Rust compile this as a DLL. If we take this out, it's going to compile it as an exe, and then obviously we can't use it in a DLL hijack attack because it's not a DLL. Okay, so that's something to be aware of. And also another thing I'd noticed, if like me, you have made the upgrade to Windows 11 and you are attacking a Windows 10 machine or Windows 10 system, you need to specifically tell it which architecture to target. So I think I've got it up here. Yeah. So whenever you do the cargo build, you need to do cargo build -- release and then pass the architecture here of x86_64 PC Windows GNU. Okay, so that's just something to be aware of, but that's well documented. So just, if your DLL is not working, that can be something to be aware of. Just if you haven't specified the architecture, depending what operating system you're on, there may be a mismatch there. So that is our basic DLL. We do then have a fancier DLL in here, which is doing very similar things. Lots of commented out code because I had a pain trying to get this working. It was a day, but we got it. And what it's going to do is it's going to execute a whoami command on PowerShell and send that out of a remote socket back to my machine. So I'm going to have an attacker machine set up, which is the machine we're currently on. We're going to have a victim machine set up, and this is basically going to run a command and send that output back. Okay, so basically to emulate the likes of a C2 connection or something like that, or a network-based connection, just to add in, that not only can we make a pop-up box, but we can also cause it to, run commands for us and do things like that. It also then helps whenever we start looking at the EDR and the defensive side of things. It'll also show you how these things can look different in those tools, and it gives us other things to potentially pivot off from a defense point of view for identifying these things. So that's that one. And then the last one that we have is a very super basic Go program that is going to start calc.exe. Okay, and this one's just compiled as a bog standard exe, and I'll show you that attack and what that looks like whenever we go over there. But very, very simple thing, and just compiled normally, because again, it is just an exe, not a DLL in this case. But you can write DLLs in Go. Again, if you're interested in that, let me know in the comments, and I'll show you how to write those as well. So let's jump over to the victim machine, which is this one here, just standard Windows 10 machine. And let's first look at how do we identify a DLL, or sorry, an exe that that we could abuse. And as I'd said, it's in the WinSxS folder. And if I go down here in the C drive, it's under Windows and, oh, wrong thing, not web, in SXS. This one. As you can see, there is an absolute ton of exes in here, or files that we can go into. Lots of different files, folders, all that good stuff. You could do a search on here, just *exe to start finding some of them. But it doesn't narrow it down that much for us, because just because there's an exe in here doesn't mean that it loads a DLL, and also doesn't mean that it's necessarily vulnerable. So how do we find them? Well, one of the things we can use is procmon, or process monitor, this tool here. If I go into the filter that I've got on here, we can see that we are looking for that the path contains D, which is the drive that I'm going to use here. So I'm under D downloads. So we're looking for something that contains that path, and the result is name not found or path not found. Original, in some of the articles, they were saying to specifically look for a create file, but I noticed that wasn't always the case, that it was a create file that it was looking for. So I've unchecked that one. But these three in particular seem to be working fine. So what I'm going to do, we have already found an exe. Okay, so to save looking through, what we would do is we'd set up that filter and then write a little program that goes through and basically just hits all these exes, from this folder. So we would run something from this folder, like a PowerShell script or a Python script, and basically tell it, hey, run through here, find any exes, run them, and then we have this filter set up and we look and identify which ones we want to go for. That's obviously very time consuming, so in the sake of speed, I've got two that we're going to look at, and then they've already been identified. So what we're going to do is I'm going to start procmon so that it is now monitoring for processes. And if I just hit the up arrow, we've got this exe here, engine task.exe. Okay, and I just want to show actually my working directory. If I go ls in here, you can see we've got a couple of DLLs and a couple of files, ICAR test files, things like that, and a folder called DLLs. But in the minute, there's nothing else in here, okay, that we need to concern ourselves with. That's important. We'll see why in a second. But if I run that, we can then see, and I can stop this now because it's very resource intensive and this is not a very beefy box. But we can see that it has popped something. You see in this case it's a query open. But it is looking in D downloads and it's looking for mscore svc.dll, and we get a name not found. Okay, that's what we need to know. That's it. Okay, we've now seen that whenever we run this command, it looks for a DLL and it is looking for it in the current directory that it was ran from. So for anyone who's not familiar with command lines and working directories and application directories, the working directory is the directory that you are currently in as the user. So in this case, d.downloads, whenever you run something. So me typing this full path to engine task exe is the same as if I was doing, say, an ls like this to get my listed directory. Really, ls has a binary somewhere, has a file somewhere that is being ran. It's just we don't need to type out the full file path every time. So if I was typing like the engine task.exe, so I just type that command name, if it was set up that way, it would then be able to, we would be able to ignore all of this C, Windows, blah, 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 and it would then call it directly. Okay, so the working directory is just the one that you're currently in whenever you run an exe. It's not the directory that the exe is in. Okay, so it's a little bit of a distinction. If you remember from the article that I pulled up, which I think if I still have it, we've got here the directory from which the application is launched. So that one is the directory that the exe is in, the binary is in. The current working directory is the one that we are in when we run the binary. Hopefully that makes sense. If it doesn't, comment, let me know, and I will try and explain it better. So this is why this attack in particular is a little bit more spicy, because it's looking in the current working directory first. So it's looking in this downloads folder, which we have full access as, and if we were an attacker on the system, we can just pick a service, or sorry, pick a folder that we have full read-write access into, and then we can use that to put our DLL in and fly under the radar, you know, whereas if we had to put it into the application directory, that might be write protected, it might be monitored, it may be more difficult for us to do. So now that we've identified a DLL that we want to attack, we can do that. So as I said, I'm in this folder at the minute. We've got DLLs and we've got a couple of other files in here. We're not going to worry about them. What we're going to do is we're going to go into the DLLs directory. If I do another ls, we can see that we've got two files here and another folder. We've got DLL shell, which is the one that's actually going to do some network-based connectivity. And then we've got mscore svc.dll. Now this is the same DLL I showed you before. I've just renamed it to match what this one is looking for. And then I've also got systeminfo.exe, which I'll show you in a wee second. And so now if I run the same command again, so it's the exact same exe, we've just moved into a different folder, which has a DLL that is the same name as this. And if I run it, we then get our pop-up, hello, get hijacked. Okay, that is how easy this kind of attack is. Okay, so just because we're in the directory that has a DLL that is the same name, it's ran it first. It's going to pop up a couple of times just as it tries to figure out why it's not working, and then it closes. So again, this obviously breaks the exe. The exe didn't run properly because our code, our DLL, doesn't have what it needed. But because we're running it manually ourselves, it doesn't really matter, you know. Whereas if we wanted to say do privilege escalation, where let's say we realize that this engine task is running on a scheduled service and it's running as an admin, and we wanted to then spawn say a reverse shell or a C2 beacon or something like that as an admin, we would then need to leverage that task. Whenever that task run, we need to make sure that that task's exe is then picking up our DLL instead. It's a different flavor of the attack and definitely another video. But in those cases, we would then be concerned about it breaking because that scheduled service is going to be there for a reason. So if it breaks something, then that can make it more obvious that there's something suspicious going on. So now that we've ran that, let's pivot over to Elastic and see what we see, if anything. So I'm under the alerts now, and if I just refresh this, and we've seen nothing. There's been no alerts raised from doing that. So what does that mean? Okay, if we were doing a red team exercise or a purple team exercise, from this perspective, just assume I'm always doing a purple team exercise, so working with the blue team in a very open way. With that, we would then look at it and see, okay, how can we build a detection for this? How can we make it that we can alert? Because ultimately that is the goal of purple team. It's to validate whether rules that have been created work, and if they're too restrictive, too narrow, or if they could be evaded. And in this case, there's obviously no rule in here that is picking up on this. Now, this isn't a, oh, this is how you can evade Elastic Defend. It's not the case. The power of these kinds of enterprise tools is the ability to write custom rules, because every environment is different. So Elastic have a really, really good stack of like baseline rules that do catch a lot of stuff and aren't too noisy, at least in my lab environment. In a production environment, that may vary. But they're not going to have rules for absolutely everything, and that would be bad if they did, because it's not one size fits all in enterprise environments. There's lots of weird and wonderful nuanced things. Maybe you have an environment that uses or WinSxS a ton for all sorts of things. then this would be very noisy if we had something that was like just looking for things being called from there. And so that's the power of doing exercises like this against your EDR systems, against your detections, to try and find gaps that then can be filled and work together and build an alert. Now, I'm not going to show how to make a rule today. Again, if that's something that you want to see, I can show you how we can go into rules and make a detection sim rule and all that good stuff. If that's something you're interested in, again, comment below, let me know, and I'll certainly do that. But creating alerts is a whole skill set in of itself, because you have to make it, not too narrow that it's then easily avoided by changing it slightly, but you also don't want it too broad that it then creates a lot of noisy alerts that are nothing. It's a whole thing. Again, something for another video. But ultimately, the upshot is that this was not detected. So, what else could we do? Well, it wasn't doing anything inherently malicious, right? It was just opening a pop-up box. Depending on what the exercise that we were trying to do, so let's assume that this was an exercise inside a company, that might be fine. That might be enough. Okay, so it might have been that they just wanted to see if someone was using DLL hijacking using this, then we don't need to do anything malicious. But does that mean that, that alert didn't fire? There was no alert for it. So does that mean the company's vulnerable? Well, not necessarily. So what we could do, if we go into DLL shell, then here we've got another DLL, and this is the one that's doing the network connectivity. So this is the one that's making a callback to our command and control, our attacking server, our attacking system, which is just the base system that's that I'm running on, which is this one here. And if I pull up this again, and let me do netcat, clear that window, and we will do this. So let's just make that bigger. So here we've got netcat listening on port 4444. Okay, and what this is going to do is this is then going to get the response back from our DLL shell. So if I pull this up again, just to remind anyone who may have forgotten, we have another DLL that's going to do the same thing. It's going to do the pop-up box, but afterwards it's then going to execute PowerShell, run a whoami command, and then send that back to our machine, which is on this IP address here, 192.168.1.152, and then on port 444. So it's the exact same DLL up to a point, and then after that we're then running this new command using the command common new, and then we are putting the results into a variable, little print line for debugging, because I had a whole thing with this. We're then creating the TCP stream, so we're then opening up the socket, and then we're sending the results back to it. So what we should see in here is it'll be victim PC / grunt. So if I actually just cancel this for a second and I do a whoami here, you can see that it is desktop grunt. Okay, but whenever we run this, this will then pop up with victim PC. I can't actually remember what I called the PC. It'll be something like that. And we'll see that connection coming back. So again, we're running the exact same command. The only thing we've changed is we moved into a different directory with a different DLL. The DLL is named the same for obvious reasons, but the actual contents of it is different. It's that Rust code that you've seen previously. And if I now run this, we're going to get our pop-up box. I'm going to hit OK on that. And if we go back, wait here for a second, and there it is. You can see we've got a new connection from that server on that port, and we can see victim lab / grunt. Okay, so it's gotten a connection back from that other machine. Now, here's the fun bit. Let's see if Elastic picked anything up now. So I'm going to refresh this, and we're going to give it a second for things to populate. Okay, and in fact it has picked it up now. The alert's a little bit strange just because I was testing this earlier on, and it basically grouped them together. Expected behavior, but just made it look a little bit funky. But if I then go in here and view details, We can then see that malicious behavior prevented network connection via process with unusual arguments. So lots of good information in here, but what we'll look at is the actual event and analyze that. And hopefully you'll notice here that what it's picked up is that the engine task spawned PowerShell and ran a whoami command with a couple of network connections. Okay, and if we go to the network start connection in here and we scroll down on the second page, and then we can see the destination address, which is correct, and the port number, which again is weird. Something to note and a question for you, so go to the comments, get ready. Has this picked up that this was a DLL hijack? Give you a second. Okay, and the answer is no, it hasn't. It hasn't picked up that this was a DLL hijack. It's seen a process do something weird that it's not usually meant to be doing. In this case, a network connection spawned with PowerShell. What that tells us as the attacker and the defender is that there's room here to maneuver. Okay, because this is very specific in the way that it's picked this up. So looking at this, it'd be like, okay, well, what if I use a different exe that maybe does spawn PowerShell normally? What if I use something that does have network connections normally? Would we then have missed this? And it also makes life difficult for the analysts, because looking at this in isolation, they don't know that this was a DLL hijack necessarily. Now, with a bit of digging, they will find, any good analyst will quickly work out what has happened here, but from the timeline that's presented from the alerts, it's not clear. Now, again, I want to stress this isn't me saying Elastic Defend is bad. This would be the same regardless of what EDR solution I was on here. They would just have a different set of pre-built rules. What I want to emphasize here is that whenever you're building rules and you're, I suppose more when you're testing rules, either with a red team, with a purple team, or if you just don't have that and you're testing it yourselves, these are questions to ask whenever you see the alert pop. Is this telling me what this attack was? Is this giving me enough information to know that this is the type of attack that it was, and I can then pivot off and do my response and quarantine it and do all that good stuff? And if the answer is no, then it needs to be tweaked. You need to pull additional information into here. You need to tweak it. And again, making sure that it's not too narrow in scope, that it then could be evaded. Because again, if I use a different exe, maybe instead of spawning PowerShell, I spawn from a command line, because I believe engine task does spawn command line, or it does use command line as a argument. It does send things to the command line. So would that look less suspicious based on this rule? Potentially. And so those are things that you need to look out for whenever you're doing it, because whenever you do a test like this, in some cases you see an alert and you're like, cool, that alerted, we're safe. Or you've looked at it and went, oh, it didn't alert, we're unsafe. It's a bit of both. It's never that clear cut. Because something didn't alert, especially from like a proof of concept, so that first one that we had the pop-up, it doesn't necessarily mean that the company wouldn't spot an attack like that going on, because there's going to be other things. Like if it's an actual attacker in the network, they're going to be doing network things like this. They're going to be running other commands, and those are maybe things that would be spotted. So it's to bear in mind that, whenever you're doing a proof of concept test, to make sure to drill in and see, okay, is this what I need to see? Okay. So now that we've seen that, let's look and see what other things we could do. And then we will, oh, it didn't like that. Connection failed. Oh, I didn't have my listener running when I ran that again. Okay, that's fine. That's that. Okay, my PowerShell crashed, so we got that opened up again. But as I said at the start, if you remember, it doesn't always necessarily have to be a DLL that is being loaded by a file. In that case, we're seeing here that there's this store diag. I think it's some diagnostic software, that if we run it, we will see not a DLL, but an exe being searched for. So again, going to use procmon here and start the capture. So again, it's the exact same filter that we're looking for. And if I run that, give it a second, and there we go. And I'm just going to stop that because it grabs a whole lot of stuff. So you can see that it is looking for DLLs. Why did that find a DLL? Oh, it did find a DLL because I'm in the wrong folder. My bad. Hold on. So, okay, yeah, the spoiler. That's what I was going to show next. You may have seen a pop-up down there saying something malicious happened. That's why. So I was in the wrong directory. I was in the directory with this systeminfo.exe. So let me run this again. And we are not seeing it. Interesting. Hold on, let me debug. Okay, not entirely sure what happened there. I just reran it a couple of times and then it popped up. So yeah, so the first time I was in the folder that I had my systeminfo.exe. So it actually just ran the exploit. As you'd seen, the same filter. We go in here, same thing. It's looking for path not found, name not found, and it's in the D drive. And you can see that it's looking for systeminfo.exe. And as you already seen, if I go into DLLs where we've got systeminfo.exe in there and rerun that, we'll see a pop-up down here in this corner. All being well, it'll flag it again once we get there. Yep, malicious behavior prevention. So Elastic Security has actually came in and stopped it from running. If it didn't do that, it would have opened calc.exe. This is the Golang code that you've seen previously. But let's go over to Elasticstack and have a look at what that looks like in there. Okay, and unsurprisingly, we do have a couple of alerts coming in. So 3 of these we know about. These top 2 look a little bit different. So let's just double check. Sure enough, it's picked up the store diag and the system info. And let's actually look at the alert itself, because this one has actually picked up that it is potentially a DLL hijack. So if we open it up, you can see malicious behavior prevented, binary masquerading via an untrusted path. So in this case, this one with the exe, it has actually picked up and said, hey, this is not the usual path for this exe. There is something weird going on. And the rule itself for this one has just got a ton of binaries in it and where they should be, and that's what's picked up. So the reason why this didn't detect the DLL is simply because the DLL was not in the list. It's the only reason that wasn't detected. So this is why I'm saying that making these rules is an art form in of itself. So that's it. That is a DLL hijack attack, particularly the WinSxS folder. That's how it works. It's super basic to do. There is plenty of other things you could do with it. We could start loading in maybe shellcode, because we know that loading the DLL in particular doesn't get caught. So we could start doing some funky stuff with maybe trying to load things in memory so it doesn't look as suspicious, or sorry, so that the EDRs just can't look at it really. We could do other stuff like that. So if you want more videos on this and show how we can expand on this piece of code, this Rust code, to run shellcode, spawn like C2 beacons, things like that, let me know. I'll happily do a video on that. And as usual, do all of the subscribing, all that stuff to try and help the channel grow a bit. But yeah, thanks for watching.